All right, and this is a excuse me, 2n squared dimensional. 2n squared in the real sense of dimension. All right. And then he goes on to say, well, you can also talk about the SL. You can also talk about SLNC. So what would SLNC mean? What do you guys think? SLNC was going to be what? It's going to be like A and GLNC such that what? Determinant of A equal to 1, right? And so you can look at this. So basically this is equal to the determinant, the kernel of the determinant, where determinant is a mapping from GLNC to the non-zero complex numbers. And because of the argument, I was just finding a way to butcher, even though it's like stupidly trivial in the middle board, because I always make a mistake 45 minutes into any lecture. It's like a law of my lecturing. That's where we are, 45 minutes into this lecture. And don't look. So.
You need something to be able to go over.
What?
You need something to be able to go over.
Oh, yeah. Thank you. So that is, again, surjective onto the non-zero complexes. By the global rank theorem, it follows that the dimension of SLN is the dimension of GLNC less the rank of this determinant mapping. Because the determinant's complex valued, it actually has rank 2. So the dimension of SLNC, and we're talking about real dimension, of course, I believe is 2n squared minus 2. And then he gives a super interesting example about the densely subgroup of the torus. If we look at that dense wind on the torus, that's a Lie subgroup. It's an immersed. That's an example of a Lie subgroup which is immersed but not embedded, because the dense wind on the torus was not immersed. It was not an embedded subgroup. All right, and it turns out, as he says here, that in chapter 20 we'll see that that issue, that like the let's say how you say this. It's typically the case that the immersed subgroups. Let me just be kind of fuzzy about it. Basically, the immersed subgroups fit inside a nicer embedded group. Like there's an embedded subgroup just sitting there waiting to find close to the immersed subgroup. It's just like a little bit. The immersed subgroup would be like dense in some embedded subgroup, something like this. But these results, he says, they're given to us in a later chapter, basically. And so, and theorem 7.21 says that if G is a Lie group, H is a Lie subgroup, then H is closed in G if and only if it's embedded. But that's not the real theorem. The real theorem is given at the end of this section, and we might as well just state that one. And this is the closed subgroup theorem, and it says what? Closed subgroup theorem. Because I'm not going to prove the weaker theorem in chapter 7 anyway, so why don't we just state the real theorem we're not going to prove? Okay, so the closed subgroup theorem asserts the following. It asserts that every subgroup of a Lie group, every subgroup of a Lie group that is topologically closed is a topologically closed subset, is automatically a properly embedded Lie subgroup. And we're not saying this theorem, I'm not saying that the data is that it's a topologically closed submanifold. I'm just saying it's topologically closed. I'm not saying anything about it being a submanifold. Like it's a topological condition is enough. Subgroup that's closed topologically is necessarily a properly embeddedly subgroup. So this is actually something that's in my thesis. One of the theorems we proved for supergroups was this. This is one of Lee's theorems. I don't know if we proved exactly this, but something akin to this is proved in my thesis. So, all right, let us go on. So, what's up next is what? Oh, that's for Jeff to say.
I was saying it a different way.
You're saying it in a different way. Oh, okay.
I said let us commence forward. And I said, let's go.
I did find a proper professional wrestler meme that has that.
Are you going to send it to us in advance?
I don't really have a way to do it. Although I did just recently discover that Gab AI has an image generator. And it's not censored. It's all right.
Oh yeah, they were censoring me when I was trying to have Jay-Z at a dinner table.
I mean, I just want Hitler to play poker with Donald Trump. Is it too much? Why can't I see that? I mean, what does it hurt anybody if I have various historical, people play poker with current leaders,
I think your video is going to be flagged.
I mean, it might, but it's probably going to be okay. Okay, so group actions. I would say up till this point, it's kind of mysterious why we even care about Lie groups. I mean, yeah, fine. We care about groups because they're interesting, and they solve interesting. I mean, groups solve interesting problems in algebra, right? Like ultimately, group theory was invented to understand how to solve, like how to generalize the solution to the quadratic formula. The fact that you can't solve a quintic equation necessitated the invention of the Galois group, which then, in the process of studying what the Galois group is, we study what permutation groups are, and once you study what permutation groups are, then just the rest of group theory that you guys study kind of falls out from that. So there was a problem, which is kind of like a high school algebra problem, understanding how to generalize the quadratic equation, which essentially birthed group theory. That's one way to look at it. The other way to look at it is that group theory was born of the need to study symmetry groups on spaces. And that's where this group actions discussion starts to really come into understanding. So the group action, what it does is we have a Lie group, and we let it act on a manifold. And so, for example, the notation is something like this. So this is a left action of G on M. And it's something like this. We take in a tuple, one in the group, one in the manifold, and we spit out a manifold entry. So in particular, we take like G comma P, and we map it to G dot P. All right, and the rules are, here's what you need for your action to be a group action. What do you think the identity should do? The Eins element acting on P should give you what? P. Very good. Exactly. And the other thing is, if we had group element 1 dot group element 2 dot P, it ought to make sense. In the sense that we could either multiply the group elements inside the group and then act on P, or we could act on P by G2 and then subsequently act on P by G1. So this looks like associativity, but it's not really associativity. It's a mixture between multiplication in the group and the group action. And so that's that. And then we usually introduce additional notation just to confuse the students. Well, I have one notation when you could have three. So theta, G cross M goes to M, and the notation is just this: theta g of p is equal to g dot p. I'm pretty sure. All right, g dot p. Yeah. And okay, so in this notation, what are our axioms? By the way, these are axioms. Axioms. What do the axioms look like in the theta notation? Okay. Theta E is equal to the identity on M, which is what you just said, right? And theta G1 composed with theta G2 is just equal to theta G1, G2, right? This looks a lot like the homomorphism property, you know? But anyway, let me behave. So, moving on here. If you have, so here's definition. M, vector space, or smooth manifold. But hey, a vector space is a smooth manifold, so I don't see the need to distinguish, you know? So, whatever. M, a vector space or a smooth manifold endowed with a metric, whatever that is, a metric or other geometric structure. So we will talk more about what that means later in this course. Okay? So if you have a smooth manifold, and in addition you have some kind of object on it which measures like distance between points or something else, this could be a geometric structure on the manifold. In this case, the set of diffeomorphisms that preserve the structure all right, and we're being kind of cagey, whatever that is, structure, is called the symmetry group of the structure. And as he says, it frequently turns out to be a Lie group smoothly acting on M. Okay, so some more, and you know, I feel somewhat bad telling you guys about factor group before Dr. Sprano does. I don't want to steal his thunder, you know. But I feel no pain. I feel no, what's the word? Remorse. That's exactly the word I was looking for.
Forget at the beginning of topology class so that we can hear it for the first time again. We will forget at the beginning of that class, whenever it comes.
Ah. So my point here was just this. The things I'm about to tell you, we don't typically cover in 421. Well, Dr. Sprano doesn't. I have in the past, but I don't do it very good. I don't do it justice either. So the orbit of P, it's G dot P. So that's the set of all G dot P such that, you know, G is in G. So basically it's all the points in the manifold which get mapped to by the group action from the point P. That's the orbit of P. There's also something called the isotropy group or a stabilizer of P. This is denoted, to make it extra confusing, G sub P, which looks nothing like G dot P, so that's good. G sub P, this is G and G such that G dot P equals to P. Let me emphasize right now the very radically different nature of these two sets. This is a subset of the manifold on which you're acting. This is a subset of the group which is acting on the manifold. Notice that by axiom, the Eins element is always in the isotopy subgroup. Oh, a subgroup, it's a subgroup. You can prove that that's a subgroup, yeah.
Is this a kernel of sorts?
Oof. A kernel of sorts. It does feel like that, doesn't it? That's a good question. What is it the kernel of? Is it the kernel? Well, the G is fixed on the theta map, isn't it? Is it the... Well, maybe, but I don't know if I've got the right structure to make that clear here. That's the isotropy. Furthermore, we say that the action is transitive. It's transitive if for any P and Q in M, there exists G and G such that what? Q is equal to G dot P. In other words, you can move from anywhere on the manifold to anywhere else on the manifold by an appropriate group action if it's transitive. Transitive actions, they go everywhere, right? Like Dr. Sprano's travels is like a transitive action. Let's cover the whole U.S., right? The action is said to be action is said to be free. All right. If the only element of G that fixes any element of M is the identity. In other words, if you've got G dot P equals to P for some P, that implies that G equals to E. Equivalently, he says equivalently, every isotropy group is trivial. It makes sense. The only thing, G dot P equals to P only for G equal to E. So this action is said to be free. Another way to say this is that G sub P is equal to the identity group for all P in your manifold. Yep.
So for some P means any P.
Yeah, just for if there exists a P. Yeah. Now, I know we're kind of short on time, so I will try to be brief here. But now I'm debating whether or not I can skip what remains here. There's a really nice calculation on page 167 I want to go through, but I probably shouldn't do that today. Let me talk about what are group actions, what are the examples of group actions here. So we have oh man, did I erase them? Guess I did. Rats. So these are not, most of the things I'm about to tell you about, they're not some newfangled thing you don't know about already. Like the central examples of group actions, Lie group actions, are examples which are familiar to you. Matrix multiplication on Rn is a really nice example. See, if we, this is actually his example B. His example A, fine. His example A is just stupid. He's like, G, any Lie group, check this out. Any Lie group, M, a smooth manifold. This is so stupid. I don't even know I'm bothering to write this on the board. It's just so stupid. G dot P equals to P for all G in G. There you go. That is called the trivial action of G on M. That is technically a group action. And in this case, the orbit, every orbit's just a single point, and the isotropy group, each isotropy is the whole of the group. So B is more interesting. This is the so-called natural action of GL, and R on Rn. And it's simply this. AX maps to AX, where we think, of course, of X as a column matrix. Is that smooth? Well, yes, because matrix multiplication smooth. And if you notice, like the identity matrix on X is equal to X, right? So, and the identity matrix is the Eins element for this one. And if you have A dot B dot X, I'll use the dot notation here momentarily. That's equal to, A dot BX, but that's equal to A times BX, but matrix multiplication is, in fact, associative. So there's the axiom 2 in this case. Now, maybe the orbits are a little bit more interesting, right? What can you say about this? Is this action, he says, because any non-zero vector can be taken to any other by an invertible linear transformation, there are exactly 2 orbits, 0 and everything else. So I guess that's fairly clear. If we think about the orbit of 0, what happens if you multiply 0 by a matrix? Right, so like G dot 0 is equal to A times 0 such that A is in GLN, which is just the set containing 0. But he claims that if we have G times X, so we're looking at, AX, such that A is, invertible matrix, he says that's everything else. So let's let Y be an element of Rn. X is fixed here. Can you tell me how to get to Y? My question to you is A times, what A times X is equal to Y? How would you construct an invertible matrix? How would you construct an invertible matrix A, which when you multiply it by X, it gives you Y? Can you do that?
Along the diagonals, is it like y1 over x1?
y1 over x1. Let's see here. Let me think about this.
It would be multiplying y x inverse, where x inverse is just.
But x is a vector. There's no x inverse.
Whatever, just be making it negative. Or transpose.
Let's see here. I think. So anyway, I think that's a good question to let you guys stew on. See if you can figure that out before next class. Right. I think I know the construction to make it work, but if I remember right, it involves like taking y and extending it to a base. So we're assuming y is non-zero, right? Well, I guess we're not assuming. We can argue in 3 seconds. Why is y not equal to 0? Because if y was 0, that would imply x is 0 because a is invertible. But we're assuming here x is not equal to 0 because the argument, if we believe John Lee, and we do, is that the orbit of any non-zero vector is everything else. It's like there's 2 orbits for the general linear groups, natural action on column vectors. It's everything or,
Could it not just be like a matrix where it's all zeros except for the diagonal line, and it's just each component of y over each component of x?
But I don't know that like individual components, if you're talking about division, I don't know that the components are all non-zero. We could take, well, x is not equal to 0. I guess I can extend x to a basis, right? That's a basis for Rn. So then if I call that beta, then the matrix beta, right? Maybe I can do something with that. It's something like something like that. You got to go. I know it's fine, but anyway, I'm going to stop here, and we will pick up here. When is it? Thursday, right? Yeah. So yeah, I may stretch out our schedule a bit. I don't want to hurry too much through this stuff. So we're almost.